What does a falling apple really have in common with the moon orbiting the Earth? The answer might sound crazy, but it's everything. Today, we're going to unravel the epic story of gravity, that invisible force that literally shapes our universe, from something as simple as an apple dropping to the grand dance of the cosmos.
All right, so here's where we're headed. We'll kick things off with the ancient mystery of why planets seem to wander across the sky. Then we'll see how a genius named Kepler finally figured out how they moved. After that, we hit the big one, Newton's universal law. And finally, we'll bring it all home and see how that very same law lets us launch rockets into orbit today.
So, for literally thousands of years, people would look up at the night sky and see a massive puzzle, right? The stars, they were predictable. They wheeled across the sky in perfect arcs. But then there were these other bright lights, the planets, and they just wandered. They'd speed up, slow down, even move backwards. The first huge challenge was just trying to figure out what on Earth was going on. And let me tell you, the path to figuring it out was a long one. For over 1,000 years, everyone pretty much accepted Ptolemy's model where Earth was the center of everything. Then, some brilliant thinkers like Aryabhata and later Copernicus came along and said, hey, what if the sun is at the center? But even they had one big thing wrong. They were all stuck on the idea that planets must move in perfect circles. And because of that, their predictions, well, they never quite matched up with what astronomers were actually seeing.
And that's where this guy, Johannes Kepler, comes into the picture. Now, Kepler had a secret weapon, decades of the most precise, detailed astronomical data ever collected, all thanks to his mentor, Tycho Brahe. With this data, Kepler wasn't trying to figure out the big why of it all just yet. Nope, he had one single obsession, to figure out how the planets were actually moving.
And after years of just grinding through the numbers, he did it. He cracked the code with 3 beautiful, simple laws. First, and this was huge, planets don't move in circles. They move in ellipses, kind of like squashed circles. Second, an imaginary line connecting a planet to the sun sweeps out the same amount of area in the same amount of time. And third, he found the precise math linking how long a planet's year is to how far it is from the sun.
So what does that second law actually mean in practice? Well, it's pretty cool. It means a planet is not moving at a constant speed. It actually speeds up as it gets closer to the sun in its orbit, and then it slows right down as it gets farther away. It's this incredible cosmic rhythm of hurry up and then wait.
So Kepler gave us the instruction manual for the solar system. He told us how it all worked, but he had no idea what the engine was. The huge why was still just a giant question mark. That is, until Isaac Newton came along, and with one single idea, explained everything. And this is where the famous apple story comes in. It wasn't just about watching a piece of fruit fall. Newton's stroke of genius was realizing that the force pulling that apple to the ground was the exact same force reaching all the way out into space and holding the moon in its orbit. There weren't 2 sets of rules for heaven and earth. It was one single universal law. And his idea was this: everything that has mass pulls on everything else that has mass. Simple as that. The more mass you have, the stronger the pull. But, and this is crucial, the farther away you get, the weaker that pull becomes. And it weakens in a very specific way, following an inverse square rule. So if you double the distance between 2 objects, the force of gravity between them drops to just 1/4 of what it was. And there it is. The key to the universe, written down in a single elegant equation. This lets you calculate the gravitational force, F, between any 2 things in the entire cosmos. All you need to know are their masses, m1 and m2, and the distance between them, r. It works for apples, for planets, for you and me, for entire galaxies. It works for everything. Now, what about that big G in the equation? That's called the gravitational constant. And just look at how ridiculously tiny that number is. This is the secret to why gravity seems so weak in our everyday lives. You don't feel a gravitational pull from your computer or your coffee mug because that tiny G scales the force way, way down. You need something with the absolutely colossal mass of a planet, like the Earth, for that pull to become the powerful force we feel every single moment. Newton's law also comes with a couple of really handy shortcuts. The first one is called superposition. It just means if you want to find the total gravity pulling on something, you can figure out the pull from every other object one by one, and then just add all those forces up. The second one is the amazing shell theorem. It basically says we can treat a giant sphere, like a planet, as if all of its mind-boggling mass was squeezed into a single tiny point right at its center. Trust me, this makes the math a whole lot easier. Okay, that's the grand cosmic theory, but how do we actually use it?
Let's bring this all back down to Earth and see how Newton's law works right here, and how it's the key to getting us into space.
You probably remember learning about g in school, right? That number, 9.8 meters per second squared, that everything falls at? Well, guess what? It's not some magic number. G is simply the answer you get when you take Newton's universal equation and plug in the mass and radius of the Earth. It's just a special case of the same law.
Now check this out, because it's a little weird. We know gravity gets weaker as you go up, say to the top of a mountain. That makes sense, you're farther from the center. But it also gets weaker as you go down into the Earth, like into a deep mine. Why? Because as you go down, more and more of the Earth's mass is now above you, pulling you back up, and that cancels out some of the pull from below. And all this leads to a really fun question. We always say, what goes up must come down. But does it really have to? What if you could throw something so incredibly fast that it just keeps going? Fast enough to completely break free of Earth's gravity forever.
Well, that speed has a name. It's called escape speed. And for Earth, it is just ludicrously fast. 11.2 kilometers every single second. That's over 40,000 kilometers an hour. Now look at the moon. Its escape speed is way lower, only 2.3 kilometers per second. And that massive difference comes down to one thing. The moon just has a lot less mass, so its gravitational pull is weaker.
And that number isn't just a fun fact. It has huge consequences. The moon's low escape speed is the exact reason it has no atmosphere. Any gas that might have been there just heated up over billions of years and easily drifted off into space, because the moon's gravity just wasn't strong enough to hold it down.
Now, for things we want to keep around, like satellites, it's all about energy. You can think of a satellite in orbit as being trapped. Its total energy is negative, which means gravity has a stronger hold on it than its own speed can overcome. It's basically in a state of forever falling towards Earth, but it's also moving sideways so fast that it constantly misses. If its total energy ever hit zero or became positive, whoosh, it would break free and fly off into space.
So, from those ancient wandering stars to the GPS satellites we use every day, it all comes down to Newton's incredible law of gravitation. He gave us the playbook. He told us how it all works with stunning precision. But there was one profound question left unanswered. What actually is gravity? What is this mysterious force? Well, to answer that, we'd have to wait for Albert Einstein.